as this warm-up is, and I think you did find it all easy. I'm sure you all got it right. Good job. And make sure you do put the denominator on there. It's not good enough to just write 5x plus 1. That would be incorrect. Okay. Those are different. Okay. As easy as this was, I do have an interesting follow-up question. This is very easy, but what if I gave you this as the question and asked you to give this as the answer? Could you do the reverse on this? That is the single question that motivates today's lesson. We're going to talk about something called partial fraction decomposition today. And your only goal for the day is that you should be able to do the thing I just said with even more complicated rational expressions even than that, right? So, for example, like this, imagine this is the problem on the left, 3x minus 1 over x to the 4th plus x squared. The goal today would be to figure out how to break this into these pieces, right? Somehow. It's kind of, already maybe you're thinking, even as I presented this question on the warm-up, how would you go backwards? You're kind of already maybe building some ideas in your head. What do you notice already about this problem, more on the warm-up? If you were trying to go backwards, what tools would you already notice and use? Yeah, you notice the factors are important, right? Like, the first thing you might do is be like, well, I don't know what's up on top if you're going backwards on the warm-up. But I do know that the two denominators are probably whatever they were. X minus 4, x minus 3, and x. Whatever. Yeah, exactly. You probably would make a good guess, and you'd be right, that those are the two denominators. And does that kind of logic follow here, too? That these denominators are all factors of the denominator on the left, right? So that's an important element, so we'll have to say something about that. But then it's a little bit of a mystery still, I think, in all of our minds, like how do we come up with the numerators? So we'll have to do some work to discuss that. So notice here, I have some words to say about what we have here too. Up the top I have this sentence. Notice that, at the very least, notice that here I have, it looks like I can decompose it into denominators that are linear factors, like x is a linear factor, right? Or powers of the linear factor, and also irreducible quadratics and possibly powers of those irreducible quadratics. I picked the easiest irreducible quadratic I could think of for this example, x squared plus 1. But so keep in mind that if you have like a denominator of x minus 3 to the 4th or something like that, then what we're saying is, that's a linear factor raised to that power, right? Does that make sense? That's what we mean by a linear factor. X is a linear factor. So that's what we're looking for in the denominators. We'll make that more explicit on this next slide. Is the task at least clear in your mind? What the goal is? I give you some arbitrary rational function, and I tell you to do this. That's what's going to happen. Right? That's where we're headed. Let me give you the easy 5-step plan, and then we'll actually do one. So these steps might be a little confusing because they're right now devoid of a problem, context, example. But we'll do an example in a second, and these things will become clear. We're not going to do one like this today. By the way, this should say if the degree is higher or equal, then start by doing long division. We're actually, I think you'll see one or two of those in your homework tonight, but just for the sake of time, I'm not going to show you one quite like that today. So if that's true, then do the long division. So once you have in your possession a rational function where the degree on top is lower than the bottom, now we can proceed. And like you guys already thought about, factor the denominator, right? Of course that's going to be what you need to do if it's not already factored. You already have this real strong inclination, and it's the correct inclination, that there's like something, the factors are going to be important in constructing these denominators in this partial fraction decomposition. By the way, this is about to get kind of crazy here. So let me just back up and motivate this discussion with two, because a lot of people, I think already maybe you're asking this question, like this seems like challenging and weird and like possibly unnecessary. So let me give you 2 reasons why a person might want to do partial fraction decomposition. All right, the first reason is you have to admit, when I presented the little backwards puzzle in the warm-up, you were intrigued, weren't you? Like you were thinking, that is an interesting puzzle, Mr. Chase. How do I go backwards? Aren't you just dying? Just like out of like the human condition, you have like a hole in your heart that needs to be filled. So there's that motivation. There's like for the sake of beauty and joy in mathematics and puzzles, right? And just like for the love of the game. That's always a motivation, by the way, in math class. But I'll appeal to that. The other motivation is not like glamorous. I hate using this motivation, but this is something you'll need for calculus. It turns out that expressions like this on the left, there's a thing we need to do in calculus that's hard when it's in that form, and it's easier when it's in this form. So, like I said, I hate like passing the buck to the next course, but that is another motivation, is that you're gonna need to calculus. Okay. All right. With that in mind, brace yourself here, because these two bullet points are a little bit heavy to swallow here. This is okay. So you already saw it on the previous slide a little bit, but for each linear factor, that might look like this. Say, for each linear factor that appears in the factorization, you need, like I said it in the last slide, is x minus 3 to the 4th or something like that. I just wrote that off to the side. You need as many copies of that over in your recipe. Every version of that up to the powers of that linear factor, up to and including the highest power that appears in the factorization. So if you had x minus 3 to the 4th in your factorization to the denominator, then in your recipe that you're building over on when you do this decomposition, you're going to need to have a denominator of x minus 3 and x minus 3 squared and x minus 3 cubed and x minus 3 to the 4th. Like, right? Is that clear? Every version in the denominators up to that power. Yeah.
Wait, is it supposed to be like for the m on the bottom of the denominator? Is it supposed to be m minus 1 or m?
Yeah, this last m should be like an m minus 1 or something like that. I knew. Are you a computer science person? Like an off by 1 error or something like that. You're picking on me. It doesn't matter what these are, by the way. Yeah, that technically should be an m minus 1, I guess, if we're like being precise. Thank you. It actually doesn't matter too much though, because whatever. They're just constants, right? Is the point. And in fact, actually, when I go to do these today, you'll see, and I think you'll maybe adopt my practice. I just usually call them like we usually have like 5 constants or something like that. I usually just use A, B, C, D, or whatever instead of subscripts, because there aren't usually very many once we actually do this. And then number 4 is a little bit hard to understand maybe, but it's actually saying the same thing as 3, except for irreducible quadratic factors. So suppose that ax squared plus bx plus c, this quadratic, suppose that's an irreducible quadratic. That is, its roots are non-real. Then you do the same thing. If that irreducible quadratic appears multiple times in the factorization, then you need to include every version of that up to the power that is on there. And then, of course, the last step, I told you it's a nice, easy 5-step process, oh yeah, we actually have to find the constants. Right? So the first thing we do is we kind of set up a recipe. We have all the denominators firmly in mind. But then we still need to establish, like, okay, now what are the numerators? What are those unknown constants? I'll let you stare at that for a minute. This is just exactly what's in the book, by the way, remember. And we are recording this. And it is under the class. Emmanuel, you have the slides back there?
It just says I can't open it.
What?
So, yeah, I can try.
Someone was able to get into the last class, so I think it's a personal problem.
I'm trying.
Maybe you make sure you're logged into MCPS.
Yeah.
Wait, do what?
He's trying to get the slides on. I do try and put all my PowerPoints up ahead of time if you ever want to print them out or whatever else. I'm just right now I'm feeling bad that like some of you are writing every word of this, which is fine though. Good. Any other thoughts? I know you'll have questions that will be cleared up on the next slide as we do a problem or two here. But Is there anything you want to say at this point, though? Okay. Anyone still need a second on here? It's under, yeah, go to the About page and then go to course document. Make sure you log into NCPI. All right, here we go. Unit 2. PowerPoint, refresh. All right, so the first, we're going to do this kind of in 2 parts here. Let's just practice writing the recipe first, and then we'll worry about step 5, solving for the constants, on the next slide, okay? But let's just practice figuring out what exactly are we even, let's define the task. Like, what are we even solving for? What are the constants? What's the form of the partial fraction decomposition even going to be? But do not solve for the constants. Good. Didn't want to yet anyway. So if you're willing to take a stab, you're welcome to volunteer. I'm willing to do the first one here for you. I don't know. If you want. And then maybe I'll let you guys try the second one. Is that a good plan? All right. So for each, this is, let's just be clear, x cubed, that's a linear factor raised to a power. It's a repeated linear factor. X plus 3, that's a linear factor that's not being repeated. X squared plus 1 is an irreducible quadratic factor, and it only appears once in the factorization. Cool. So here we go. I'm just going to try and obey the instructions on the last slide, step 3 and 4 on those, right? So for every linear factor to the m, or to the third, or whatever it was, you need to include all of these things in our recipe. Something, a constant over x, plus a constant over x squared, plus a constant over x cubed. Do you now understand what I mean by we need to have every version of the linear factor up to the power, up to the number of times it's included? Okay. All right, let's keep going. And then we need for x plus 3, that's another linear factor. So we're going to have a d, constant d over x plus 3. And I guess I didn't really stop to explain why this is necessary. But this is an irreducible quadratic. So the denominator will be that. But the numerator will be, did you catch on the last slide? Did you see the slight difference? It's going to be e x plus f. And this is not a full explanation, but here's a little bit of some reasoning around this. The question is, how good can you get in these numerators? If you have a linear factor in the denominator, suppose that the numerator is linear. Well, if the numerator was linear, like say we couldn't assure that this was a constant. Well, if it was a linear, something linear, why isn't this dx plus e over x plus 3? Well, if it was linear, then already I know we could do better, because couldn't we do long division if the degree is the same, if it's linear over linear? So I think already I'm pretty convinced that for any linear factors, I can just have a constant on top. But I can't make that guarantee for something quadratic. Can I assume that this isn't quadratic? Yeah, I think so, because if it were quadratic up top, then I could have done more division, right? I could have made things simpler, and I'm assuming right now that everything is as simple as it can be. So I think the best we can assume here, though, is linear on top. So does that make sense? We need to have the numerator we're assuming has at least degree 1 less than the denominator. So now that still complicates what about these, Mr. Chase? Well, I haven't thought about it enough to answer that question. Okay. Do as you're told. No, I don't know. Let me think some more about that. But okay, that's all it was asked there. Write the form of the partial fraction decomposition. If one actually wanted to solve for the constants, you'd have 6 unknown constants to solve for, and you could do it. It would be okay. It's a lot of constants to solve for them. Go ahead and try B if you haven't already started. And check when you get your answer. Check with the other people at your table. See. Check with the other people in your group.
So let's start with negative 1.
Are you supposed to just like say
Just a lot of letters.
Are you supposed to separate it?
And say instead of the alphabet. A over x plus 2.
Oh wait, I think okay.
5.
Over x minus 2.
King dog plus cx goes to
Bad.
cx plus d over x squared plus 3. That's the linear.
All right, you have it. You check with people in your group. I don't want to spoil it for anyone. That would be tragic. All right, here we go. So, wait. I have an answer key, and their name is Daniel. Go ahead, Daniel. What do we say?
A over x plus 2 plus b over x minus 2
How's he doing so far, everybody?
plus cx plus b over x squared plus 3.
How did you do, everyone? Oh, wait, you're not done.
Plus
There's more?
x plus f over x squared plus 3
Have you done this before?
x squared.
Kind of gave it away by putting the parentheses on top where he said squared.
Well, he was going to do that, right?
Yeah, I have it first.
See? Right? Does he have a Corinne? He does? Okay. See? Eight. That's correct. Again, if you were to go and solve for the constants, you would have 6 constants, unknown constants to solve for. Some of you might be confused again about why these 2 things are necessary. Again, it's the same logic as we used up here. If a linear factor appears 3 times in the factorization, you need to include every version of that power up to that power, right? The same exact thing goes for irreducible quadratics. If an irreducible quadratic appears twice, like it does here in the factorization, then you need to include every version of it up to its power. Okay. All right. Let's actually do one here. This will look like the setup. The recipe will look like child's play on this one. This is nice. This is a nice one to start with. So let's do the setup, but this time we're actually going to go all the way and solve for the constants. So, go ahead. When you're ready. Am I right? This one feels easy now. Actually, this one.
Yeah.
As far as the setup goes, Laura's gonna give it to us when she's got it. Very good. She's checking her answer. How did it go? How did the review go? Did Oren approve? Okay, say that. Okay, so this was x minus 5 and x plus 3 over here. Okay, great. Now, some of you, keep in mind, some of you might have the constants different than hers, but we're going to go with Laura's constants because she's in charge. Okay. So hopefully you can translate, or if you want to change yours around to match this, that's fine. Great. So here we go. Let's see if we can figure out what the constants are. Let's keep in mind at all stages of this process that what we have here is not a conditional equation. That is, this is not an equation that is only sometimes true for certain x values. What we're making the claim that this is always the same as this, right? These are the same expressions, right? You could plug an x value, x equals 10 in, and you get a true statement involving an a of b. Anyway, so just keep that in mind, that this is like an identity. This is a statement that's always true. So I'm going to multiply both sides by the denominator just because I'm not a fan of fractions. Do you follow that I get this? So far, so good? Let me remind you one more time that this is an equation that I can plug any x value into, and it will give me a true statement. So for example, I could plug in x equals 50, and I would get a true statement. And notice that if I plugged in x equals 50, it would be a true statement involving no x's, only a and b, right? It's an interesting observation, isn't it? Isn't it? Let's be as lazy as possible, though. What x value would you like to plug in? Zeros? I can even, maybe we can even be lazier, though. What'd you say? Yeah, what'd you say? 5, right? Let's let x be 5. Like I said, you can plug in x equals anything, and you'll get a true statement involving a and b. But just because we're lazy, let's let x be 5. And let's see what happens. If you don't see yet why that's a slick choice, you're about to. Okay. If all right, so what do we have? We have 24 is equal to 8a. I think we're about to know what a is. It's 3. Returning back up to the equation that led us into green pastures so nicely, and that was beautiful. Let's just do that again. Let's have a second course, okay? You want to plug in -3? Sounds great. You can plug in anything you like, but if we're trying to be lazy mathematicians, then we'll plug in maybe -3. Just for fun, let's let x be -3 and just, see what happens. On the left, we get -16, right? And on the right, we get -8a, -8b. Yeah. You following? So we have a, and now we have b. What is b? It's 2. All right, now keep in mind, do not, maybe I shouldn't have put boxes around those. Do not leave that as your answer. Make sure you answer whatever was asked. Because clearly, again, I don't know if some of you had different constants. Your a was 2, and your b was 3 or something. So it's not necessarily clear what we mean. I want to make sure you can actually connect the dots here. So what do we have? Let's make sure we get these in the right place. 3 over x minus 5 plus 2 over x plus 3. And that I'll put a box around. That's my final answer right there. That's the partial fraction decomposition. We did one. Hey, look at that. Yeah, okay. How could you check your answer? Yeah, this just was the warm up in reverse, basically, right? So if I asked you to add these back together, hopefully you would get the original expression. So if you have an extra minute on your test or something like that, I don't know that you will, but if you did, then that would be a great use of time, right? And then you could walk away knowing that you're right. Be like, I can't possibly be wrong on that question. I definitely got that all right. That would be a good feeling to have. All right. Let's try another one.
How did you know I wanted this for my birthday?
I know. Is this your birthday?
It was last week.
Oh, that was Friday? Yeah. That's right. I remember you saying. There, I did the factoring for you. You're welcome. You're welcome. I just factored it for you. That's just the kind of guy I am. There you go. Saved you a lot of work. I'm ready to hear from my favorite student, Robin. Okay. What's the form of the partial fraction decomposition? Give me the recipe, the setup. Whoa, hold up. You factored it. This is what I'm looking at now. I like the a over x. I'm keeping it. Do you like it? You like it? All right, well, if you like it, let's do it. Here we go. I'm going to do the same thing as last time. I'm going to multiply through by this denominator. 5x squared plus 7x minus 4 equals a times x squared plus 4 plus bx plus c times x. All right, do you agree with that? So far, you're following the algebra here? Unfortunately, as you're looking at this, you're so excited to do that math. By the way, the last method we used is called the annihilator method. You like that?
Annihilator method.
It's also called the Heaviside Method, named after the guy who did it, who suggested that method. So yeah, it's called the Annihilator Method because for obvious reasons. Boom, get rid of the A, or boom, get rid of the B. But we can't really do that. Are you already looking at this? I mean, you still could do the same kind of approach. Let X be a number and plug it in and get a true statement involving A, B, and C. But you can see that there's not an immediate route to that here, right? So I'm going to introduce a second method for solving for the coefficients. And this method works all the time, always. It's not quite as cool, maybe. I don't know. Actually, I think you're going to like it. Here we go. I'm going to multiply out the right side. By the way, let me remind you again that what we're working with here is an identity. That is, this is always a statement that's true for every x value, okay? Multiplying this out gives this. And I'm going to go one step further. I'm going to collect like terms on the right side. So we have a plus b is the quadratic coefficient. And c is the linear coefficient. And 4a is the constant term. There we go. All right, now let me just say it again. What we have here is the same thing on the left and right. This is an identity, right? That is to say, the polynomial on the left is the polynomial on the right. And what's the aha moment you want to share?
A plus B is 5.
A plus B must be 5. Right?
B is 7. A is A1. Oh my goodness.
Right? I mean, if they really are the same polynomial on the left and right, then I think we can make that conclusion. So this method is called, I'll give you a name now. I didn't want to give it away because the name gives it away. It's called the method of corresponding coefficients. Okay? So this is, and this will work on the last one too. In fact, this method that we're just now using will work on all problems. It's just the annihilator method is kind of fun when you only have two constants. It's pretty slick, right? All right, so in general, when we do this process, we're going to get to this point and we're going to have a system of equations. Here we have a system of equations, 3 equations and 3 unknowns, right? Imagine doing one of the ones we did previously with 6 unknowns. You, at the end, have 6 equations and 6 unknowns, right? Now, I just want to give you a caution. Your book asks you to, if you actually look in the book section, like if you're like, ooh, I'm not sure I understood the lesson today, and you look back at how the book presents it, they turn to heavy machinery to solve these systems of equations. They like suggest using matrices and loading them into and solving using a matrix method, which maybe you're familiar with. But that's not necessary here, right? Like I think I'm good here. In fact, it's hardly a system at all. I already know C. Now I know A, and in a second I'll know B. What's B? Isn't that fun? Okay. And then, of course, remember that's not the answer. The answer is, here, we'll put it up here. The answer is -1 over x, let's get these in the right places, plus 6x plus 7 over x squared plus 4. And again, if you wanted, you could check that that's the truth by adding them together. It's actually not too bad to add together really quickly. You could do it. It's -x squared minus 4 plus 6x squared plus 7x. It's going to work, yeah. So I mean, that's actually not very, sometimes it's very quick to check, actually. Hard to do, this process. The other way is pretty quick, isn't it? So, at least write this down before you go. I think the bells, aren't we here till? Oh, no. We have 10 minutes. Sorry, sometimes I forget which period it is. Good. I was like, you really need another example. All right, good. Let's do this one. I'm going to try and be a little more hands-off on this one. I want to see how you guys do. Yeah, you might want to check in with your group before you do the whole problem. Right after you get the recipe, right? Just so you make sure you're not like going off on a problem trying to solve with the wrong setup.
Okay, I got it. Ready? Here we go. Over here.
Right.
AX plus B over X squared. Cx up is
ax plus b over x squared plus 1 plus cx plus d over x squared plus 1. Right?
Wait, okay, I was on board until you like kept going.
And then you, since that's squared, it's going to be this squared under here. So this squared is this squared.
When you put that square under there. No, see, you don't have to do all of that. Look at this.
Creating some new constants.
Look at this. Look at this one. When there was the whatever.
Oh, you're right, right.
Is it less complicated than that?
It probably is.
Okay, I'll just roll with this and deal with the consequences.
Oh wait, that's much neater. Okay, so
By the way, do you know why sometimes we use capital letters? A lot of times in math, we use capital letters for constants. Things that are not variables. For constants.
X squared plus y squared.
alright, boy is right. We'll get to it. Yes. Oh,
No, I'm not.
maybe the two. Okay.
Yeah, those things.
I think everyone had this set up right as I walked around for the most part. So I'll write that up here.
That's it.
I think I made some of those constants come out kind of nice.
I think I did a thing. Does this look like literally simple thing?
I just try a lot.
Yeah.
Sorry,
A plus b times x squared.
cry is cry is don't cry. Oh.
Yeah, I know.
Is a bike
Did you win? Did you win?
I got 4th place.
Question place.
Wait, so I built my target, and then you got another spoon.
you know where it came from?
I know, he got another spoon.
Yeah. That'd be good to feed someone wrong information about you. Oh, the safety today.
Oh my god, I had an
You're like the
idea.
only friend of yours that shows up. It'd be good to like feed someone like wrong information about. Oh, the safety monitor. Everyone's bringing off their record. Tell your friend that. Nobody would do that. I mean, okay. Maybe I was being extreme. All right, how are you doing on this? Did you finish? How's the algebra going here? Do you agree so far with the algebra, right? And then multiply out the right side, collect like terms, do what we just did, right, on the previous slide. Whoa. I think you'll find that like some nice, I made this one somewhat nice.
I just took the complicated route for nothing.
Erasing everything. All wrong. Yes.
You can only do the linear term, right? Which was missing.
Because ax even says x squared plus 1y is there squared out.
Oh, I did multiply it out really wrong. Okay.
Okay, I'm collecting like terms.
I did the wrong way. But I did it right, I don't care. I did it wrong.
There are no other x squared terms.
Okay, I did it right.
Like I said, this is actually not too bad, is it? Right? There's lots of stuff that's 0.
Yeah, it's like just on the edge of the first.
All right. So what's a? Yeah, a is 0 because there is no cubic term over here. B is 3. Like I said, you thought you'd have to solve a system of equations in 4 variables. Well, you kind of do, but not really. A plus c is 0, and yeah, we can already make the conclusion then that c must be 0 since a is. And b plus d is 4, apparently. That's the constant term. And we know b is 3, so d must be 1. All right, so I think we're ready to rewrite this now. Here we go. So it's zeros. By the way, this will not always happen. I just thought it'd be nice. So we get a, which is 0 times x plus b, which is so 3 up top, plus over here, was that 1? How you feeling about this, people?
Wait, why can't we take a plus squared before and then
How did you
plus
think
d
that?
equals 0?
Yeah? Add them back together if you're not sure.
I understand this.
Okay, it is a little bit weird, this process.
How do you take
Okay, why can't a plus c equals 4 and then e plus d equals 1?
So a plus c is the thing that's times x, right? And that's there is no linear term over here. It's 0x, isn't it? So that must be the coefficient. Yeah. Here? Yeah. So if you multiply through by x squared plus 1 squared, that clears it out of here. Agree? When you multiply by x squared plus 1 squared here, it clears one of them but not the other, so we still have one, don't we? It'd be like multiplying like 1/3 by 9, right? Like one of the 3's goes away, but you still introduce a 3 then, don't you? It's like canceling out one of them. And here, both of them cancel out here as well, right? Does that make sense? Yeah. Chris,